The idea of a linear combination of vectors leads us to consider the collection of all linear combinations of a collection of vectors. And that's called the span of the vectors. So suppose we have some subset of vectors living S living in a vector space V. Then the collection of all linear combinations of those vectors in S is called the span of S. So here the span of S is every linear combination of vectors in S with coefficients, of course, in the real numbers. So, you know, this way of writing it might look complicated, but really this is just a sort of very symbolic way of saying all linear combinations from S, of vectors from S, right? So looks tricky when you sort of write it out precisely mathematically, but the idea is just you take vectors from X and mix them together in every possible way using linear combinations. By convention, incidentally, the span of the empty set, so this symbol here is the set that has no vectors in it, the span of a set with no vectors is the zero subspace, so the subspace consisting only of the zero vector. So, you know, this conceptually, I guess it makes sense, but what does it really mean? I mean, if you think about vectors in 3 space, this gives you, I think, a good, strong indication of what span is actually doing. So in 3 space, which I'm gonna, it's a little hard to draw 3 space on a plane like this, so work with me. Suppose we had 2 vectors in 3 space, right? What would the span of these 2 vectors look like? Well, if we take all linear combinations of these 2 vectors, that means we could follow this vector, and then we could add the other vector, and that would get us this vector, right? So there's a vector in the span, because that's 1 plus the other. Or we could follow this vector twice this vector, and then follow the other vector, like this. That would give us this vector. Or we could go half this vector and then half that vector. That would give us this one. Or we could, you know, by following all linear combinations, you can sort of see that all linear combinations, here let me name them, V1 and V2, all scalar multiples of V have to be in this, V1 have to be in the span because, right, we have right here, we can have any coefficient, any scalar in front of V1. So here are all of the scalar multiples of V1. But then also from any one of these, we could add any scalar multiple of V2. So for any vector aligned with V1, we could follow any multiple of V2. So that would give us all of these. So, right, we can get to any point along this line, but also any point along this line, and any point along this line, and so on. What we're really doing here is just sort of stretching each one of these vectors out and sort of blending them all together. And what that does is it kind of fills out the plane that contains V1 and V2. So, you know, what we're seeing here is, at least in R3, the span of 2 vectors is the plane that contains them both. Containing both. Although there is an important caveat here that it's the plane that contains them both when V1 and V2 aren't collinear. Right? If they're collinear, then the span actually turns out to be just a line. But anyway, so, you know, when I think of a span, what I think of doing is having each vector, stretching them all out, and then kind of blending them all into each other to kind of fill the spaces in between. You can see that, right, there are vectors in R3 that are not in this span, like this one out here, right, that sort of casts this shadow on the plane. Because V1 and V2, because the span of V1 and V2 can only get you anywhere in this plane, there's no way to get up out of this plane, right? V1 and V2 always stay in, multiples of V1 and V2 always stay in this plane. So there's no way to get up out of this plane, and so there is no way to get this third vector as a linear combination of v1 and v2. So the span of v1 and v2 is not the whole space R3, it's just this, this plane. Incidentally, some sources use this notation for subspace, just square brackets, but I would say that that's less common than actually just writing the word span, so I'm going to keep writing the word span. All right, so just to make sure that we understand what span actually is, let's ask a question about it. So in this vector space, P2, so this is the collection of polynomials of degree less than or equal to 2, is this polynomial, x squared plus 17x minus 11, in the span of these two over here? Well, asking if something is in the span of two vectors, what that's really asking is our polynomial x squared plus 17x minus 11 a linear combination of the other two? Right? Everything in the span of these other two polynomials is a linear combination of these two polynomials. So really we just need to know, is this polynomial a linear combination of the other two? How could we check that? Well, as usual, everything will come down to solving a system of linear equations, but let's see why that is the case. So if our quadratic is in the span of the other two, right? So if so, then that would mean that x squared plus 17x minus 11 is equal to a linear combination of the other two. And a linear combination is some scalar times the first one, x squared minus 3x plus 1, plus some scalar times the second one, x squared plus x minus 2. Okay, now, so why does this turn into a system of linear equations, you might be asking? How is it that polynomials can be equal? Well, polynomials are equal only when coefficients on corresponding terms are equal. So maybe what we should do to clarify matters a little bit is group like terms on the right-hand side. So on the right-hand side we have, let's see, for our x squared terms we have a coming from this one and b coming from that one, so a plus b times x squared. And then for our x terms we have minus 3 coming from this one, sorry, minus 3a coming from this one, and then plus b coming from that one times x, plus, and then for our constant terms we just have a minus 2b. Okay. Now, polynomials are equal only if coefficients on corresponding terms are equal. So that means looking at the left-hand side, the x squared term is 1, and on the right-hand side, the x squared term is a plus b. So we need a plus b to be equal to 1. And then looking at x terms, we need minus 3a plus b to be equal to 17. And then looking at constant terms, we need a minus 2b to be equal to negative 11. And now you can see this is, sure enough, a linear system, and we can solve it in the usual way, write down the augmented matrix and row reduce. So 1, 1, 1, minus 3, 1, 17, 1, minus 2, minus 11. And then this doesn't look so bad, so I'm going to go ahead and row reduce it, but you know, I wouldn't blame you if you fast forwarded this part. So 1, 1, 1, and then so second row plus 3 times first row, so 0, 4, 20, and then last row minus first row, 0, minus 3, minus 12. Okay, now we can maybe divide the second row by 4. So 0, 1, 5, and then 0. While we're at it, why don't we divide this row by minus 3? So that's going to make it 1 minus 4 plus 4. Yes. Okay. And then, So now we can do first row minus second row, 1, 0, minus 4, and then leave the second row alone. And then third row is third row minus first row, so 0, 0, minus 1. Okay. Now remember that what this row is saying is that 0 times A plus 0 times B is equal to minus 1. Well, this isn't true, so there are no solutions to this system of linear equations, and that means that it's impossible to make this true, and that means that this is not in the span of those, because it's not a linear combination of these two. Okay, so again, span is just a compact way of referring to all possible linear combinations of some vectors. All right, one other question about span. Do the vectors v1, which is 2, minus 2, and v2, which is 3, 4, span all of R2 or only a proper subspace? So here, proper means a subspace that isn't actually the whole space. So subspace means a subspace that's actually smaller than R2. So how could we check? Well, to know if these span all of R2, we need to pick sort of a generic representative of R2, and that would look like AB. Right? And then we need to know, is it possible, or is AB, our generic representative of R2, a linear combination, or is it in the span of V1 and V2? In other words, is AB a linear combination of V1 and V2? Well, this is a question we know how to answer, right? We have seen before that what we can do, if we want to know if one vector is a linear combination of other vectors, all we need to do is solve a linear system that looks like, right, x1, v1 plus x2, v2 equals the vector that we're aiming for, which is AB. All we need to do is solve this for x1 and x2, and we saw that this is just a linear system whose augmented matrix is 2, minus 2, 3, 4, AB. Right. So to know if this has solutions, well, we can just solve it, just row reduce. So let's add the second row to the first row, so R2 plus R1, 2, 3, A, and then minus 2, 0, 7, A plus B. And now I'll stop right here because so this is not a reduced row echelon form, but this is a row echelon form, and we can see from this row echelon form that there will be solutions. In fact, there will be exactly one solution. So there is a solution. Right. If we wanted to actually know what that solution is, we would need to continue solving this, but this row echelon form is enough to tell us there's a solution. So in other words, there's a way to pick x1 and x2 to write AB as a linear combination of v1 and v2. So AB is in the span of v1 and v2 for every choice of A and B. Right? A and B have to be real numbers, but every vector in R2 is of this form. So R2 is contained in the span of v1 and v2. Of course, R2 contains the span of v1 and v2. Right? V1 and v2 are vectors in R2. every linear combination of vectors in R2 is in R2, so the span of v1 and v2 also is in R2. So R2 contains the span and is contained in the span of v1 and v2. So that means that this span of v1 and v2 is actually exactly equal to R2. So maybe it wasn't obvious at first, but now we see that the span of these two vectors is actually all of R2.